Example 6, two three-phase loads are connected in parallel and supplied at 480 volts. Load 1 is 15 kilowatts, 0.7 lag power factor, Y connected. Load 2 is 18 kVA, 0.8 lag power factor, Delta connected. The feeder from the source has an impedance of 0.25 plus J 0.5 ohms per phase. Determine A, the voltage regulation when these loads are supplied, B, real reactive and apparent power drawn from the source, C, the power factor of the source, and D, efficiency of transmission. So once again, we have to make some assumptions. Our first assumption is that V line is 480 volts. Our next assumption will be that V phase will be our reference. So that is going to be V line over the square root of 3, which equals 277 with an angle of 0 degrees in volts. And that is going to be our reference. So now let's draw a diagram that represents this system. So here we have the voltage source for the system. Here we have the impedance of the feeder or the line, 0.25 ohms, J 0.5 ohms. So this is for one phase. And then here we have our two loads. So we already said that the voltage across the phase will be our reference. So that means that V phase here is 277 with an angle of 0 degrees, and the units are volts. This is load 1, and this is load 2. So since load 1 is 15 kilowatts, 0.7 lag power factor, that means it's, when you divide by 3, it's going to be 5 kilowatts per phase and 0.7 lag. For load 2, you also have to divide by 3. So the 18 kVA is going to be 6 kVA per phase. And that one's going to have a 0.8 lag. So here's the equivalent circuit for one phase. So now we're going to have to use our power triangles in order to find our other values. So let's do a power triangle for load 1. So here's the triangle, and we're going to put the values that we already have on it. So I'm going to have 5 kilowatts here. And then I need to find the angle that goes here. The angle that goes there is the arc cosine of 0.7. The arc cosine of 0.7 is 45.6 degrees. So now, if I want to find Q, Q would be equal to P times the tangent of 45.6 degrees. So it's 5 times the tangent of 45.6 degrees. And that's going to be in kVar. So Q is equal to 5.1 kVar. So the complex power for load 1 is 5 plus J, 5.1 kVA per phase. So next we need to sketch a power triangle for load 2. So for load 2, the hypotenuse of the triangle is 6 kVA per phase. And then we need to find this angle here, which is going to be the arc cosine of 0.8. So that angle is 36.9 degrees. Where this is Q and this is P. And so what we're going to have here is that P is equal to 6 cosine 36.9 degrees, and that is going to be kilowatts. So P is equal to 4.8 kilowatts per phase. And Q is equal to 6 times the sine of 36.9 degrees. So Q is equal to 4.8 kVAR per phase. So S2 is equal to 4.8 plus J 3.6 kVA per phase. And so then when we add those together, the total complex power at the load would be 9.8 plus J 8.7 kVA per phase. So that's in rectangular form. We write that same answer in polar form, then the total power delivered to the load will be 13.1 with an angle of 41.6 degrees kVA per phase. So now, if we want to find I, we know that the current through the load should be S over V conjugate. So that's going to be 13.1 with an angle of negative 41.6 degrees divided by 277 with an angle of 0 degrees. So the current through the load is 47.3 with an angle of negative 41.6 degrees. And the units are amps. So the phase voltage at the source would be equal to 277 with an angle of 0 degrees plus the feeder impedance 0.25 plus J 0.5 times the current 47.3 with an angle of negative 41.6 degrees, which equals 301.8 with an angle of 2 degrees. So then the voltage at the source in terms of the line voltage would be the square root of 3 times the voltage at the source phase. So that would be the square root of 3 times 301.8. So the magnitude of that source voltage as the line voltage is 522.8 volts. And that's the magnitude. So then the voltage regulation is going to be V gen or V source minus V load divided by V load times 100. And you can do this with either the phase voltages or the line voltages and get the same answer. So you could do 522.8 minus 480 over 480 times 100. Or you could also use 301.8 minus 277 over 277 times 100. And both answers would give you 8.9%. So next we're going to find the power drawn from the source. So the power drawn for the source, the real power would be the square root of 3 VL IL cosine of theta. And remember, that's always our phase voltage. So that's going to be the square root of 3 times 522.84 times 4 times the cosine of 43.6 degrees. Note that 43.6 comes from 2 degrees minus negative 41.6 degrees. And so the real power is 31.1 kilowatts. The reactive power, Q3 phi, is the square root of 3 VL IL sine of theta phi. So that's going to be the square root of 3 times 522.84 times 47.3 times the sine of 43.6 degrees So the reactive power is 29.5 kVAR. So now the power factor is lagging because Q is greater than 0. And so the power factor would be equal to the cosine of 43.6 degrees, which is 0.725 lag. And note that that's the answer to part C. And the apparent power is the square root of 3 VLIL, or the square root of P 3 phi squared plus Q 3 phi squared. So the apparent power is 42.8 kVA. So the final step is to find the efficiency of the transmission. This is letter D. So the efficiency is eta is equal to P load over the phase power from the source times 100, where P load is going to be 3 times 9800 divided by 31.1 K times 100, and that's the same as 29.4 K divided by 31.1 K times 100. So the efficiency of transmission is 94.5%.